Welcome to Programming Problems Episode 3. Today we will be looking at a problem from CodeChef called Pokemon Battles. Let's get started. In this problem, we are presented with N Pokemon trainers, which shall be numbered from 1 to N. Each trainer has only a single Pokemon, with which it participates in a contest. In this contest, battles will be fought in 2 arenas, one in ground, one in water, and each Pokemon can have a different power depending on the arena. When 2 Pokemon fight in an arena, the Pokemon with the higher power in that arena wins the battle. It is guaranteed that there shall be no ties. The total strength of a trainer is determined by the number of other Pokemon that they can defeat in at least one of the arenas. Now, after the first rounds of battles, only the Pokemon trainers with the highest strength will qualify for the next round. Note that it is possible that multiple trainers end up with the same strength. So given the number of trainers and the strengths of their Pokemon in the ground and water arenas, how many trainers will qualify for the next round? For this problem, we are presented with the following inputs and constraints. There can be up to 1,000 test cases in a single input file. Every one of these cases has between 2 and 10,000 trainers participating in the contest. For every trainer, we get 2 values which represent the strength of their Pokemon in one of the arenas. For convenience, we can name these arenas A and B, and the strength values which we get are between 1 and 109. Furthermore, remember from the problem description that there would be no ties? It is guaranteed that the strengths per arena are unique. Finally, we are ensured that the sum of N, the number of trainers, will not exceed 200,000 when summed over all test cases. Let's see what we can do after we examine the examples. Starting with example 1, if you look at the table, then you see that the top row represents Arena A, the bottom row Arena B. In the table, there are also 2 columns, which are visually highlighted by the rounded rectangles. These columns represent 2 trainers. Trainer 1 has a Pokemon with a strength of 1 in Arena A and a strength of 3 in Arena B. Similarly, Trainer number 2 has a Pokemon with strength of 3 in Arena A and a strength of 4 in Arena B. Now what we can see is that Trainer 2's Pokemon is the strongest in both arenas, so he will always win from the other trainer. He therefore beats one other Pokemon, though he does so in both arenas, and has a strength score of 1. Only one trainer advances to the next round in this example. Here's example 2. Please have a look at the strength values of these Pokemon. What we can see is that both trainers defeat each other in one of the arenas. Therefore, both trainers manage to beat one Pokemon, and they both qualify for the next round. In example 3, we can see that the first trainer's Pokemon is the weakest of all Pokemon in both Arena A and B, so he will always lose. Since he will not qualify for sure, we can ignore him. The other 2 trainers, however, are in a similar setup as example 2. They both beat each other once, and hence 2 trainers qualify. Let's look at the last example, which is a bit more complicated than the others. I shall give you some time to look at the table so you can take it in. Since the table is so small, it would be possible to just compare the results of each possible matchup. But there are also some observations which we can make here. For instance, Trainer 3, who has the Pokemon with strengths 5 and 1, is the strongest of all trainers in Arena A. Since there are 5 trainers, he will therefore have a strength of 4. Similarly, Trainer 5's Pokemon is the strongest of all in Arena B. Thus, Trainer 5 also has a score of 4. Now, is there another trainer who manages to get this score? Turns out that, yes, there is one. Have a look at Trainer 4. His Pokemon has a strength of 4 in Arena A and 5 in Arena B. In Arena A, he only loses to Trainer 3, who was the strongest there, but he still manages to beat 3 other Pokemon. Then, in Arena B, he actually won against the Pokemon from Trainer 3, bringing his total to 4. In conclusion, in this contest, 3 trainers advance to the next round. Now, how can we construct an algorithm for this? We can start by taking the brute force approach to explore the problem a bit more. The main goal is to figure out for each trainer how many other trainers they manage to beat at least once. So, intuition might tell us that we simply need to compare all trainers. which would work, but we possibly have 10,000 trainers, and doing such a comparison is on the order of n squared. Then, even if we manage to reduce the constant somewhat by iterating more cleverly, we still have to consider that we could get 1,000 cases, of which multiple instances could be our worst-case scenario. So, unfortunately, n squared just isn't going to cut it. We have to think of something that is a bit faster. Maybe we can leverage that the strengths are unique, so technically if we sort the trainers by their strengths, then we know their rank for a given arena. And their rank directly corresponds to how many other trainers they manage to defeat, at least in that one arena in which they are sorted. Though we cannot simply just find the rank for a trainer in Arena A and then in Arena B, because this does not directly tell us anything about the possible overlap of the trainers which they manage to beat. We'll need something more. Let's take a look at some insights. First up, hopefully we can all agree that there shall always be at least one trainer who beats all n-1 other trainers. It's simply the trainer with the strongest Pokémon in an arena, and one Pokémon could be the strongest in both Arena A and B. Moreover, we just learned that the rank of some trainer X in Arena A already tells us how many trainers are defeated there. With this knowledge, we only need to know how many other trainers, to which was lost in Arena A, this trainer X can beat in Arena B. So we managed to reduce the problem to where we don't care about strength, but about rank. Now for the final piece, can we find a way to efficiently check how many of the victories in Arena B were against trainers to whom was lost in Arena A? I'm sure we can. Before we dive into the solution, maybe you now have enough inspiration to solve this? If so, please pause and give it a go. We'll wait. Now, let's assume we're all back and see how we can solve this problem. Let's take example 4 and sort the trainers on rank in Arena A. We will sort them from left to right. After sorting, we will get the following order. Now let's iterate over the values for Arena B in reverse. The first trainer we know beats all other trainers in Arena A, so his strength in this example is 4. When we move to the next trainer, we know this trainer beats 3 other trainers in Arena A based on his rank. So all we care about is how many trainers whose Pokémon is weaker in Arena B are to his right in this list. In this case, we see a Pokémon with Strength 1, and thus we know that this trainer beats an additional opponent. Let's move to the next trainer. For this trainer, we know based on his rank that he only beats 2 others in Arena A. If we look to the right for Arena B, then he only beats the trainer whose Pokémon has Strength 1. So, in total, this trainer beats 3 opponents, which is his strength value. Essentially, what we are doing is partitioning the list in a left side and a right side with the trainer for which we want to compute the strength value as the pivot point. Again, in Arena A, we know how many trainers we beat by rank. But in Arena B, we need to find an efficient way to count the number of Pokémon strengths which are weaker than that of our current trainer's Pokémon. Multiple efficient solutions might exist here, but I've chosen to make use of an AVL tree, which is a form of a self-balancing binary search tree. We will dive deeper into that concept in a future video, but there is a lot of material out there from which we can learn. Please see this tree as merely an example. In short, a self-balancing binary tree, such as the AVL tree, efficiently manages the height of the tree as we insert nodes. Thus, the cost of most operations which we perform on such a tree are proportional to its height. Because the tree is self-balancing, this height shall be limited to the log of n. The key to make an AVL tree work for this problem is that we can augment the nodes in an AVL tree to store the total number of smaller nodes already in the tree when inserting a new node. So for the example, we start with an empty tree and then insert one. We then find that there are 0 smaller nodes already in the tree. Next, we insert 5, and we find that there is 1 smaller node. After that, we insert 2, and we again find 1 smaller node. Next up is 4, and inserting this would efficiently give us back that there are 2 smaller nodes. Lastly, we insert 6, and we find that there are 4 smaller nodes. So what about the runtime? To make this work, we first have to parse the list as input, which is simply order of n. A bit more expensive is the sorting of the trainers, which most common sorting algorithms achieve in order n log n. Then, we again parse over the trainers, but in reverse, which is order n. And for each iterations, we then perform a log n insert operation, giving us, again, n log n. And that's the final runtime, which is fast enough to solve the problem. Thank you again for following along. If you had not found it already, the link to the problem is in the description. Please be sure to leave a like and/or subscribe if you like this content, and let me know in the comments if you have any good ideas for this or other problems.